This is a pre-lab introduction to Lab 6, the lab that is going to get you started on using MATLAB. And what I have here is a sample MATLAB write-up. Never mind the fact that it says Lab 2, that is from a past occurrence of this lab. And so I just want to give you a little introduction, as I won't be there to walk you through this, but Mr. Boston will be there to help you. So here on the resource page there is a link to Lab 6. This is actually going to be a 2-week lab, so you get both week 7 and week 8 to work on this. Okay. So on the lab page there are instructions right here, and that's a PDF, and then there is some sample data that you're able to use just when you're testing things. You're actually going to use your own data, and I'll tell you about that in a minute. There's also a sample input script that you may want to use, though not necessary. And then lastly, there is a sample write-up that I'd recommend that you look at. And actually, I'm going to walk you through or show you this sample write-up. This sample write-up here that's provided, it's PDF, is actually just filled with screenshots, so it's not text, so you can't copy it and paste it in. Okay, but you're welcome to look at it and to follow the syntax and so forth. Okay, so in this lab, before we look at the instructions, I just wanted to point out that there's two caveats, two changes that I want to make sure that are important that you note. One is that although the lab refers to working with RC first order low pass filter data, just like you did last week for the MathCAD lab, instead what I want you to do is to use your data from Lab 2, where you collect the data on the Salem key low pass filter. Okay, so use that instead of the first order RC filter. You can use this sample data, just for testing things out in case you don't have that data handy initially. And then secondly, I want you to use the publish feature of MATLAB to generate HTML output, and then ultimately actually PDF output. And I'm going to show you a demonstration of that. So let's open up these instructions, so at least you can see the format. Let's go. Okay, so you can see that, I think. All right. And so what's the point of this lab? We want you to learn to create, you're going to create a MATLAB script. You're going to run the script to generate output plots. You're going to document the output in a word processing edited document, okay, that will initially be produced by the publishing feature of MATLAB, and then you're going to save the whole thing to PDF and submit it on Moodle. Okay. By the way, you're going to do this lab individually. If you took the data for the Salem key filter together as pairs, that's fine. You share that data, but I want you individually to do this work, as it's important that you each individually learn how to use MATLAB. Okay. So the objectives for this lab are to study frequency response concepts of linear systems. This is a rehash. You should be really comfortable with this at this point. But again, it's repeat or reinforcement. So secondly, it's going to be particularly to study the frequency response of the low pass filter Salem key filter, not the RC low pass filter. And then the key to the lab is to learn how to use some of the basic MATLAB tools for studying linear systems, in particular to describe a linear time invariant system, that's the type of systems we've been looking at, via a transfer function description, to be able to generate Bode plots, step responses, and impulse responses from that transfer function. Use the MATLAB's LSIM to basically simulate a linear system to an arbitrary input. This is analogous to the ODE solver that you used in MathCAD last week to solve or to simulate or numerically solve the time domain response of the RC filter to a square wave input. You're going to actually do the same thing in this lab, except it's going to be using it's going to be applied to the Salem key filter. D, to learn how to import data from Excel using XLS read command, and then import data from delimited ASCII text like a CSV, comma separated value file using the DLM read command. Okay, so in the end what you're going to be doing is putting together a MATLAB script that, when executed, does several things. It will use the description of the Salem key filter to generate some plots automatically. That is the Bode plot, step response, impulse response. It will run simulation using LSIM to predict the response of the filter to a square wave input. It will read in data both from an Excel file and from comma delimited data, but that data you're reading is going to be the data you collected in Lab 2 for the Salem key filter, and you'll bring it in and you'll plot it along with the theoretical Bode plots. So that data that you collected in Lab 2 was Bode plot data, magnitude and phase, and you're going to do the same thing. Okay, so this is just like, there's a repeat here to what you did in MathCAD. But again, you're using the Salem key filter data, not the RC filter data. Okay, so going down here, I'm not going to go through this procedure at this point because you can read through this on your own. Okay, I'm going to show you the results instead so you can get a sense of what this looks like in the end. And it's fairly detailed, steps you right through it. There's a few questions, so please note the questions that are asked. And then here are some things for the write-up. Again, the key thing that might not be clearly stated in here is that I want you to do the write-up, the electronic submission via publishing in MATLAB, and then doing post-editing of that file in Word, and then ultimately saving it to PDF and uploading a PDF. So let me show you that. Well, let's scroll down to the end of this, and then I'll show you the actual sample model. So if I was there in lab for these 2 weeks, we would spend some tutorial time where I would be up there and show you some things, right at the prompt, and then you could try them out. I won't be able to do that. Mr. Boston might be able to do that, but I'm not sure if he's going to get the chance to brush up on MATLAB. So things to guide you here is, in case that doesn't happen, is to look at this list of commands and know that these are the types of commands that are going to be used in your write-up, in your lab activity. So you can do some research on your own, okay? And the way you can do it is this first command called help. If you just type help and then space and then you put in one of these command names, it'll actually come back and ask you. It'll give you a bunch of information right there in the command prompt. If you want a more formatted graphical view, then instead of typing help, you can type doc space and then the function name or command, and then a separate help window will open up where you will see a lot more detail. So MATLAB has good help, and I think you're going to have to use that in this case since you're going to be doing a lot of the learning on your own. However, to help you or guide you is this list of commands here, rather than just kind of having it wide open. These are the type of commands that you'll want to check out. Okay, I think that's the end of that. But make sure you read through this. There's a couple tips in here that are intended to help you avoid some pitfalls in the lab activity. Now, of course, you could just take the example that I'm going to post and just copy it, but that would kind of miss the point because you're trying to learn this and become familiar. So try not to just copy it. Try to understand what's going on and write it on your own, and then if you get stuck, then go back and look at the solution, but don't just copy verbatim, otherwise you're not going to meet the learning objectives here. Okay, I'm going to switch over to MATLAB. I'm running MATLAB 12. The MATLAB that's on the computers there's 15, so it's got a different look, but the functionality is basically the same. So what you're going to want to do is, let me actually do one other thing here. Let me pull this over here, the way I have this laid out. I've got, hold on here. Okay, I'm trying to squeeze in a little bit of this editor view and then this command view all at the same time. Let me pause and make sure I'm actually recording. Am I recording? Okay. So you know that you can just type things in at the command line, right? So I could say clear. That clears all my variables. CLS clears the screen. I can now define, like, x equal to 2, 1, y equal, let's do x equal to 2, y is equal to 4, and then I could say, y to the x, and it evaluates it. Okay, now that's fine for short things, and there's a history. I use my up arrow and down arrow, and I can get through there really easily. Oops, that's loud. Okay, however, there's a better way for when you're putting a lot of commands together and you want to run it repeatedly and save what you've done. You can go to the editor and open up a script. So I'm going to open up a script, and now I can, let me give it a name here, test script. And then we can save it, and I'll save it here. Now you're going to give it a name. One of the things that'll trip you up if you don't realize this at first is that you cannot do it. Whatever you give for a name in a MATLAB script, it cannot look like a math expression. So if I go test hyphen, what did I call this? Test script. Test hyphen script, that looks like I'm subtracting, doing the arithmetic of test minus script, and MATLAB will not like that. So you have to use something like underscore. You can't start with a number, and yeah, so just keep that in mind. We save MATLAB scripts as a .m, so I'll save that. The comment is a single quote, or a single percent sign. You'll see the use of double percent signs in a little bit. But let's say I wanted to do the same thing that I just did here in the command window. I would, let's clear my variables first, and then I would say x is equal to 2, y is equal to 4, and then I could just say whatever, z is equal to y to the x, and I can save this. And now if I run this, I click this run button. Oh, okay, it says, do you want to add, it'll ask you this oftentimes, do you want to add the path where this file is saved to your working path? Say add to path. Okay, and it just ran, and here's the result, z equal to 16, because I put semicolons for the rest of these. Okay, so that's how you can save. You can use a script file, and that's what you should do here. You should be building a script file instead of doing everything at the command window. Now, to publish things, it's really nice. You can use this publish command. It might look different on the MATLAB 15, but here it is. It looks like this. You should find it. If I click publish, okay, it does a little something here real quick, and now what does it show me? It shows me this output that happens to be an HTML output. All right, this is the output that it generated. It included the script, and then it included the output that I put in there. All right, very nice. Now I can do things like, let's say, I'm going to do a double percent now. I say section 1, or I'll just say 1, some variable declarations. Okay, or yeah, let's do this. This is not necessary, but just to show the point here, say clear memory, post this here, paste this here, then 2, some declarations, then we'll go 3, some expressions. Okay, and I'll take those off. Save that, publish it. Okay, now what does it do? Because I put the double percent signs, it actually creates a table of contents. And although it's not, well, yeah, so it's actually hyperlinked. I was going to say it doesn't, you might not see the benefit here, but because number 3 is off the screen, when I click on this, it will jump to that, right? So when you design your MATLAB script, if you make use of these double percent signs, it actually know that whenever you have a double percent, it actually adds an entry into this table of contents. And so you can actually have a really nice navigable HTML file at the end. So now if I wanted to go edit this in Word, what I would do is I would go find it. Where did I put it? I put it in 15. Test script, and it creates an HTML folder. I right click on there and say show in Explorer, and then I'm going to open this in Word. Okay, and now here it is in Word, saved as HTML, and I could put in my own content. All right, so I can just put put my name here. And now if I want to save it, and then what I would tell you is save it as a different name. If you save it the same name, then you run the risk that if you run the script, if you run the script again, it's going to overwrite this, and then you'll lose all your word edits. So I've saved it to a different name, and now I can just simply do a save as, or publish to PDF. And once I save it to PDF, okay, what's nice is I actually have a PDF that has links in it. Right, isn't that nice? So this is what I would expect you to use as your procedure for generating a formatted report. So your report's going to be done completely in MATLAB initially, and then you can do further edits in Word. And I'm not even saying that you have to do them in Word, because you could very well just put in enough comments within your script here that you don't need to actually do any further editing in Word. Okay, so I'll leave that up to you. So before I let you go, let me actually run this example script. Okay, so this is, I'm not giving you a copyable version of this. Is this the LSIM simple? No, that's not the one I want. Here it is, right here. So this is my solution to what we're just calling Lab06. And it is for the RC filter, but you'll do it for the Salem key. It has the same structure. Okay, and so as I scroll down, you'll see, let's see, I've got some setup, clearing variables. I defined some variables here. I'm actually defining my transfer function right here, numerator, denominator, and this is where I define my transfer function. Okay, so you're going to do the same thing but for a Salem key filter. And so your numerator and your denominator will be different. Particularly your denominator will be second order, right? At this point here, RCLPF is a system, and I can do lots of things with it very easily, very powerfully. I can get a frequency response by simply calling Bodhi and passing it the system. I can give it a title. I can turn on a grid. There's a number of things you can do. And then I can ask for a step response. Very easy, one command. I can ask for an impulse response, all right, and then I can do some simulated response, and here you have to look at the procedure for what I'm asking you to do. But essentially, I want you to run the simulation. I want you to apply a sinusoidal excitation to your filter at it looks like 1, 2, 3, 4, 5 different values from 0.1 to 10, okay, and apply different free sinusoidal frequencies, and then plot what is the sinusoidal steady-state response. Now here's the caveat. These number values here were chosen based on the first order RC low-pass filter. I don't know if they make sense for the Salem key low-pass filter that we did in Lab 2. So I'm going to leave it up to you, and maybe Mr. Boston can guide you on this, but to pick values that basically will generate time domain sinusoidal response at frequencies that are below the corner frequency of the filter and above the corner frequency of the filter. And I would say one that's right at the corner frequency. If you remember, the filter that you designed or that you built actually had a little bit of peaking right at the corner frequency. So it would be nice when you generate these plots that you would show what does the filter response and time domain look like for frequencies that are well below the corner frequencies, that are maybe just a little bit below, and then that are right at the corner frequency. See, you'd have some peaking there, and then a couple points above the corner frequency. Okay, I'll show you what that looks like for this case in a minute here. So that's what this whole section is. Okay, and then now down, let's see, down here we're now going to have simulated response of the system to a 75% 5 kilohertz pulse train. Again, you're going to need to choose 5 kilohertz may be fine. I don't remember at this point, but the point is you should have a response that looks interesting. I mean, if this is such a high frequency that the output looks like a flat line compared to the square wave or the 75% duty cycle signal that you're putting in, then what's the point? Okay, so this generates a time domain simulation. The simulation actually occurs right here. Okay, one command, y, the output is equal to linear simulation, and you pass it the numerator and the denominator of your transfer function. What is the input? And that's what all of this is before we're actually generating basically this square wave or this pulse. And then what is your independent variable? Time. Okay. And then here's a section on importing data from the spreadsheet. So here we're importing data from Excel, and then later you will import data somewhere down further here. You'll import data from a CSV file down here. Okay, and you plot it along with your theoretical data. Alright, now let me go up here and we'll publish it. So I click the publish button. Oh, one other thing I have in here, after every time I call to plot something like Bode or step, I put in a command pause. Alright, so these are two different commands, grid and pause, but they're separated by the semicolon, so I can put more than one on a line. Every time you give it the command pause, that particular graph will stay on the screen until you press a key. So in generating the publishing report, I could turn all those off, so it would just, you'd click it once and bang, 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 just go right through it, and the next thing you would see appearing would be the published report. But I left this on because a lot of times when you're at least debugging it, you want to see these figures before the final generated report. Alright, so here we go. Click that. So you see the first plot, that's the Bode plot. And let me show you one thing that would be of interest. See down in the bottom corner here, it says, you look always down by the start button in your MATLAB application window. It says paused, press any key. So if ever things look like they're just kind of died and nothing's going on, look for that and see maybe MATLAB is waiting for some input. So I'm going to put focus on this graph, and now I'm going to press enter. The next one comes up. That's the step. Here's the impulse, and I'm pressing the enter each time. So here's that time domain response, okay, to different sinusoidal frequencies. And what I've done here, and what you're going to be asked to do, is that although the input, sinusoidal input, is changing in time, in other words, and you can see it right here, the pole frequency for this RC filter is omega p, whatever that is for this particular design, I don't remember. This first plot is, it corresponds to an input excitation at a frequency of 1/10 of omega p, right? And then by the third one, you're exciting it at omega p. So here it is, right here, and it should be at a phase shift to 45 degrees at that point. Okay, and here's the input, the triangle. Now I'll note there is a 2 pi error in my math here. Let me see if I can find it. Okay, yeah. So just make a note of this. I know it won't mean much to you now, but just put a mental note. Here I say frequency is equal to this kx. It's just this scalar here, right? A weighting times omega p. Well, omega p is calculated way up above here as 1/tau. So it's radians per second. Okay, it's radians per second. I should not have called this frequency, or I should have called it frequency underscore like radians per second, or angular frequency. That's what it is. Okay, and what happened is later, when I use this to generate the input x right here, instead of just putting frequency times time, I do 2 pi times frequency times time. What I should have put is probably what I would do here if I were to correct it at this point, in this expression for frequency, I would divide omega p by 2 pi here. Okay, so just make a note of that. That is an error. So what's interesting about this plot here, the way I have you generate it, is that if we were to just to plot the, instead of plotting a normalized horizontal scale, which you see right here, it's normalized by the period. And if I didn't do that, then when you looked at the response to 0.1 omega p and 10 times omega p, they have a 2 order of magnitude, a factor of 100 difference in period. So if you wanted to see a full period of this 0.1 omega p, fine, but then the 100 cycles of the 10 times omega p would just be a blur. It'd be all overriding each other, just would look like a small, solid, up and down squiggle. So instead, I have you normalize the horizontal axis, and that way you can see the period of a very low frequency and a period of a very high frequency on an equal time basis, if you will. Okay, so let me hit enter again. We'll move on to the next plot. Here is the time domain response due to applying a 5 kilohertz 75% pulse, okay, to our filter, to the RC filter. The response is this triangular, it's exponential response, but there's also a DC value to it because there's a DC value, an average value to that pulse. So here again, if it makes sense to do 5 kilohertz for the given Salem key filter parameters that you used in Lab 2, fine. If you get something that looks, wildly different than this, like you can't see any triangle at all, then I would say change the frequency and use something that makes sense. Okay, now is where we're going to import the data from Excel. And those are the red dots that are being plotted over top of the calculated data. Okay, and then lastly, this is one where we're going to plot the theoretical amplitude, magnitude plot versus experimental, but in this case I read it in from a comma separated value file instead of an Excel file. Okay, so just ASCII. All right, and then that's it. So now what I have is the output of the publishing, and you get this nice, it's a nice report, and it even has there's some text that goes in here, so we can go back and look in the script to see how that was put in there. That's under 2.1. What's nice, it's all hyperlinked, so you can just move right to it. You can even put links here within your text. So lastly, let's go to 2.1 and see how I did that. I don't even remember. Yeah, well, it's just more comments underneath that. So a double % gives you a hyperlink and puts it in the table of contents, and then every other comment basically gets formatted. So you could do your full report all in MATLAB and then publish it. And ultimately, though, what I want you to submit is a PDF. Okay. So I think that should be enough to get you started. And sorry for the long video, but I think this will help you to get on your way. So I hope it goes.